In the final question, we are looking at normal distribution again, and we're given the time in minutes taken by men to run a marathon, which has a mean of 240 minutes and a standard deviation of 40 minutes. So if we're going to set this up, we've essentially got T, which is normally distributed, with a mean of 240 and a standard deviation of 40. We're asked to find the proportion of men that take longer than 30 minutes. So again, to start with a quick sketch, we know that this is the mean here. So essentially, we're trying to find this probability here somewhere. So again, simplest way of doing this is on your statistics calculator. We are going to be looking at the cumulative normal CDF, the cumulative distribution function, between 300 and, again, as this is asymptotic, this would go up to infinity. So your lower boundary would be 300, and your upper boundary would be some kind of proxy, so 9 times 10 to the power 99, or something equally large. The mean is going to be 240, and the standard deviation is 40, and that ends up giving you a value of 0.0668 or 6.68%. In part B, we've got Nathaniel, who is preparing to run and wants to come in the top 20% of male runners. We're asked to use the model to estimate the longest time that Nathaniel can make to run the marathon and still be within the top 20%. So this question is kind of flipping the previous question on its head. This time what we want to do is find out the minimum time, so let's call that value t, that he can run such that he is still in the lowest 20% or 0.2. So we're doing it the other way around. This is the inverse normal distribution, so you're going to go to your calculator. The area is always the area to the left. Here it's not a problem because quite clearly we can see the area to the left is going to be 0.2. The mean is 240 and the standard deviation is 40. And if we substitute that in, that is going to give us an answer of 206 minutes is the slowest time that he could run and still be in the top 20%. In the final part of this question, we turn our attention to the times for women's marathon running. However, we're not actually given it as a number as we were in the first part for the men's. We are just told that the probability that the women's time is less than the mean plus 30 is 0.82. So here's some value here, the mean, and here's a nominal u plus 30. If the probability that a woman's running time is less than this is 0.82. Well, we know that in this region here, we know this is going to be equal to 0.5 because that's the mean, so half of it is beneath it and half of it is above it. So if the total, if the probability that the woman's time is less than u plus 30 is 0.82, the difference, i.e. this region here, let's just do that another colour, this region here must therefore be the difference between 0.82 and 0.5, so this region here must be 0.32. We know that because of symmetry, if this region here is 0.32, then similarly this region here between this value u minus 30 and the mean must also be 0.32. Now we've said that everything to the left of the mean is 0.5, so if this is 0.32 we can work out this is 0.18. So this represents the probability that the women's time is less than u minus 30, which is what we've got here. However, we want the probability that women's time is less than u minus 30 given that the women's time is less than the mean. So we've just set up here actually that the women's time is less than the mean. Well, that's going to be 0.5. So our final answer is going to be this value of here, 0.18, divided by all of the outcomes where w is less than the mean, which we know is going to be 0.5. And if we do that, we get an answer of 0.36.